Hi there, and welcome to this lesson. In this lesson, we'll be learning about thermal expansion, okay? And under thermal expansion, we're learning about thermal expansion in solids. So thermal expansion in solids. Now, as the lesson progresses, anything you don't understand, be sure to contact your tutor, who would be more than happy to help. So yes, let's jump right into the lesson. Thermal expansion in solids. Now, what exactly is this about thermal expansion in solids? Basically, the idea here is if you have a solid body and you apply heat to that solid body, okay, or basically there's a change in the temperature of that solid body, or there's an increase in the temperature of that solid body, the body would expand. Okay, so the higher the temperature, the more the body would expand. And basically, this is where this originates from. Basically, if you have any solid body at all, this solid body is made up of small particles. Okay, very microscopic level particles. You're not visible to the naked eye. But then these particles are in a constant state of vibration, so they're actually always in motion. So every solid body you can get hold of is made up of small particles that are in constant motion, always in motion. Okay, but then as you can't perceive this with the naked eye, you can't see this, but then made up of particles that are in constant motion. And these particles for solid, they vibrate about a fixed point. So they're just there, moving, vibrating about a fixed point constantly. Now, if we apply heat to a solid body, so when we apply heat, it provides kinetic energy to that body. Okay, kinetic energy to the particles in that body. Okay, so heat energy is converted to kinetic energy, and then these particles become kinetically charged. Okay, and they have energy in them, and they can move even faster. They move even more vigorously. They vibrate more vigorously, and basically they tend to do this over a larger distance, okay, and in turn causes their intermolecular an increase in their intermolecular separation. So when the particles are vibrating, they tend to do this over more, they tend in more space, they become less dense, okay, they become less tightly held together, and this is what we observe as expansion. Okay, and basically we're just going to understand exactly how this heat translates to expansion in solid bodies. And there are three forms of expansion, so three ways bodies can expand. We have linear expansion, area or superficial expansion, and volume or cubic expansion. And you probably guessed linear expansion is expansion that occurs along the length of a solid object. Okay, area or superficial expansion across its area, and volume all around the volume of the solid object. And now, something very, very important. Now, different solids expand by different amounts. So if you apply the same heat to three different solids, let's say you have aluminium and steel, if you apply the same amount of heat to two different solids, they would not expand in the same manner. They will not expand by the same amount. Basically, aluminium should expand more than steel, because aluminum is less dense than steel. It makes sense that it should expand more. But the idea is that there are certain properties of certain materials that make them expand more or less than other ones. Okay, so they do not expand by the same amount, and it's basically based on what that material is and what the properties of that material are. And basically, we bring those properties together, we sum them up for each material, and we call this the coefficient of expansion or expansivity. Okay, and this is what determines how different solids expand when heated. For example, aluminium has a coefficient of expansivity. It's fixed. It's a number. It's fixed. You often give it when you ask to solve questions, expansivity questions. So aluminium has its own expansivity, steel has its own expansivity, brass has its own expansivity, copper has its own expansivity. So different metals, different solids have different expansivity values. And basically, we're going to talk about expansivity for the three forms of expansion: linear, superficial, and cubic. So we start off with linear expansivity. Okay, and linear expansivity of a body is the change in length per unit length per unit rise in temperature. Okay, so we have a change in length. Okay, and this change in length is often a percentage, let's say a percentage or a fraction of the entire length of of that solid. For example, if you have a solid that's 10 meters long and you have another one that's 100 meters long, if they're the same solid and you apply the same amount of heat to both of them, okay, basically you would have the 100-meter long expanding made possible by 10 meters and the 10-meter long one expanded by 1 meter, basically. So expansivity, expansion is dependent on the actual length of the body and also dependent on how much heat you apply. So the difference in the temperature, how much the temperature rises. So the linear expansivity of a body is a change in length per unit rise in temperature. And basically we write it like this. So we have expansivity as alpha equals L2 minus L1, where L2 is the final temperature, L1 is the initial temperature, okay, divided by L1. L1 is the initial temperature multiplied by the change in initial length and final length. L1 is the initial length, and then theta 2 and theta 1, we have theta 1 as initial temperature and theta 2 as final temperature. So expansivity is L2 minus L1, change in length, divided by L1 per unit length, basically divided by theta 2 minus theta 1 per unit rise in temperature. And so we often prefer to write it in this manner. Okay, so instead of L2 minus L1, we say delta L. Delta L means change. Delta means change, so change in L divided by L1 multiplied by delta theta, change in temperature. Theta stands for temperature, so delta theta is change in temperature. That's it, basically, linear expansivity. And you're often asked to calculate possibly the change in length. You could be given the expansivity, given the temperature, given the initial length, and you're asked to calculate its change in length. You just work, change your subject formula, and you should have that the change in length should be expansivity times the initial length times change in temperature. And basically, you should be able to use this to calculate all of these parameters whenever asked to. Now, let's talk about superficial expansivity. It's pretty much the same thing, but in this case, we're going to be talking about area. So superficial expansivity is the change in area per unit rise in temperature. And it follows the same formula, but this time we'll call super expansivity beta, and beta is A2 minus A1 divided by A1 theta 2 minus theta 1, where A1 is the initial area, A2 is the final area, theta 1 is the initial temperature, theta 2 is the final temperature, and we often write it in this manner. Beta, our superficial expansivity, equals delta A over A1 delta theta. Okay, simple, straightforward. Let's do finally cubic expansivity, follows the same idea, but cubic expansivity is the change in volume per unit rise in temperature. So we have cubic expansivity we represent with gamma. So gamma equals V2 minus V1 divided by V1 theta 2 minus theta 1, where V1 is your initial volume, V2 is your final volume, theta 1 is initial temperature, theta 2 is final temperature. And just like linear and superficial expansivity, we often write it in this manner. Gamma equals delta V divided by V1 delta theta. And yeah, let's go ahead now and solve some examples. Example 1. And example 1, we have the main span of San Francisco's Golden Gate Bridge. Okay, so Golden Gate Bridge in San Francisco, San Francisco, is 1,275 meters long at its coldest. Okay, and so we have this bridge, the Golden Gate Bridge, and it's 1,275 meters long at its coldest when exposed to the coldest temperature in the area. And we've been told that the bridge is exposed to temperatures ranging from minus 15 degrees Celsius to 40 degrees Celsius. Okay, so these are the two extremes. Okay, so it goes between minus 15 degrees Celsius and 40 degrees Celsius. So, and basically we have that it is 1,275 meters long at its coldest. So this would be at minus 15 degrees Celsius. Okay, and we've been asked what is the change in length between these temperatures. Okay, so what we're asking now is from minus 15 degrees Celsius, if it's heated up to 40 degrees Celsius, what will be the change in length? Assuming the bridge is made entirely of steel, and we're given the linear expansivity of steel as 1.2 times 10 to the power of minus 6 per Kelvin. Okay, per Kelvin, that's the unit for expansivity, okay, per Kelvin. And we just go ahead and solve. So we have linear expansivity is delta L divided by L1 delta theta, okay. And in this case, we're looking to find delta L. So delta L is alpha expansivity times L1 times delta theta, change in temperature. So we have alpha, we're given alpha as 1.2 times 10 to the power of minus 6. L1 is 1275 meters. Delta theta. Now, when you're working with temperatures, it's very important that you convert to Kelvin. Okay, so now typically we should convert to minus 15 degrees Celsius to Kelvin, and if we do that, we just add 273, and we should end up with 250, 250 59, I think, 259 Kelvin. Okay, basically 273 minus 15, 273 plus minus 15. And we do the same with 40 degrees Celsius. We'll end with 273 plus 40 should give you 313 Kelvin. And then you subtract the 2. Okay, and if you subtract the 2, you should end up basically you added 273 to one, you added 273 to the other one, and you subtracted the two. It's pretty much the same as just subtracting the numbers as they are. Okay, so but typically when you're working with temperatures, or if you've posed with questions where the temperature, it's not the change in temperature, but the actual temperature in itself, you most definitely have to convert to Kelvin. Okay, but in this case we're working with a change in temperature where we actually subtract the temperatures, so it's not really necessary that we add 273 to both of them. Okay, so we just go 40 minus 15 and we have 55 Kelvin. Okay, does that make sense? Yeah, let's go on. So we have our expansivity, our length, and our change in temperature. And we're just going to calculate delta L as 1.2 times 10 to the power of minus 6 times 1275 times 55, and we end up with 0.84 meters. Okay, and basically look at it, it's not even up to a meter, it's actually very small. So when this bridge is heated to the highest temperature, highest possible temperature in the area, it doesn't really expand by much, okay, compared to the entire length of the bridge. But if you were asked to construct this bridge and you did not take this information into consideration, okay, this very small 0.84 meters will be basically compared to the full length of the bridge. If you do not take this into consideration and you do not account for the expansion of this bridge, the bridge probably wouldn't last very long, basically, because it will continue. It will continue. There will be forces when it expands, and there's no room to expand into. There will be forces acting on the bridge, and over time, the bridge will start to crack, and over time, the whole thing will just all come running down. So basically, if you're an engineer and you're asked to construct a bridge, and you're given the temperature range of the area. Basically, it goes from minus 15 degrees Celsius to 40 degrees Celsius. You most definitely need to take linear expansivity into consideration, okay, and factor that into your plans. So you create a bridge and give allowance for times when the bridge actually expands as a result of thermal expansion, heat changes. And then yeah, let's do another example. So very, very important stuff we're learning at the moment, okay? Millions of lives at risk. So yeah, let's do another example. Example 2. And example 2. And okay, not millions of lives, but basically pretty much everyone that would be on the bridge at any instant in time. But that's all by the way. So an aluminium solid has a volume of 10.85 meter cube. Okay, determine the volume of a brass solid if the difference in volume of the two solids is to remain constant for all temperatures. Okay, so the difference in the volume of the solid is to remain constant for all temperatures. So the temperatures are the same. What it's saying is for all times when the temperature is the same, the difference in volume must be the same. And in this case, we're looking to find V1 for the brass. Okay, and we're given the cubic expansivities of aluminium and brass at 6.9 times 10 to the power of minus 5 per Kelvin and 5.7 times 10 to the power of minus 5 per Kelvin, respectively. Okay, so where do we start? Now, we have that gamma, our cubic expansivity, is change in volume divided by initial volume times change in temperature. Okay, and we have basically, if we work that, we have change in volume divided by change in temperature would equal gamma times V1. And the reason I've done this, the reason I've expressed the formula in this is because we're told that volume and temperature are constant. Okay, change in volume and change in temperature are constant. So the only two varying parameters in this question are the volume of of the solid and of the solids, basically aluminium and brass, and their cubic expansivity. So cubic expansivity for aluminium is 6.9 times 10 to the power of minus 5 per Kelvin. Cubic expansivity for brass is 5.7 times 10 to the power of minus 5 per Kelvin. The volume of the aluminium body is 10.85 meter cubed. The volume of the brass body we're looking for is, okay, so we start off with the aluminium body, okay, and we say delta V of the aluminium, change in V of the aluminium body over change in temperature. Basically, you have delta V over delta theta equals gamma times V1, and our gamma for aluminium is 6.9 times 10 to the power of minus 5 times the initial volume of the aluminium body, 10.85 meter cube. And when you work that out, you end up with 7.487 times 10 to the power of minus 4 meter cube per Kelvin. Now, let's do for the brass, okay? And when we work for the brass, basically we have VB. We don't know what VB is. So this equals gamma times V, and we have gamma for brass as 5.7 times 10 to the power of minus 5 multiplied by the volume of the brass body. And that's what we're looking for. Now, how do we solve this? Basically, we have information that says the volume of the two solids is to remain constant for all temperatures. Okay, so if you just take a particular temperature, the temperature for both metals is the same, and the volume is to remain the same, i.e., the change in VA equals the change in VB, and the change in theta A equals the change in theta B. So we change delta VA over delta theta A equals delta VB over delta theta B. Okay, and then basically what you have for the first one, you have for delta VB over, from what we did from step 3, we have 5.7 times 10 to the power of minus 5 times VB, and this equals, from the result from step 2, we have 7.487 times 10 to the power of minus 4. And when we work that out, we end up with VB as 13.4 meters cubed. And this is the volume of brass. Basically, if you have a 13.4 meter cube brass solid and a 10.85 meter cube aluminium solid, if you heat them to pretty much any temperature at all, they would expand by the exact same amount, okay, based on their initial volumes. And that would bring us to the end of this very simple lesson. You can go ahead now and attempt questions on the worksheet. Bye for now.